So you are able to see the screen, right?
Yes, sir.
Yeah. So anyway, I think last class, so we have discussed, I think, in great detail about functions of random variables. Okay. So this we have almost discussed, like, so this was a fundamental thing. Like if you have one variable, how it will handle. Then if there are, two functions of random variables, then how you will handle. Then, so like variety things we have seen. Two functions, then functions of two, then, so you have to introduce, auxiliary variable also. So we have seen in great detail. Okay, so all those details, like this, what is it? We said that's the functions of, two random variables also. So like this, we have seen, so you can solve like basic expression remains the same, but only thing is when you're having two or three followed, right, you will have this type of Jacobian matrix, and then if it is a 2D, this one says, so you have to do this convolution integral also. Okay, so this we have seen in our last class. So that was one thing. That is, one is transformation of the random variable, that is a probability density function. Now another thing also which is very important is, the functions of the movements itself, like, how movements gets transformed. Like if I know x, say, okay, if I know its mean value and standard deviation, so here we are not interested in the their individual probability density, say. We are interested only in the movements, and then y is a g of x, say. Okay, so now how mu y and sigma y. So here we are not interested in their probabilities, but we are interested only in their movements. Okay, so that also we have seen, like, if we have linear transformations, how the mean value and then how the standard deviation is looks like. Now if we are having several random variables, say, like, a1 x1 plus a2 x2, so then mean of y will be, you can write in this type of format, and the variance is say. So you will have this type of expressions where you will be having this covariance term also, which comes into our calculations. And then if you have multiple random variables, then also, you can do this type of transformations also. Okay, so now let us see some simple the examples. Okay, so like, let us say the earthquake losses, for example. Okay, like you see, now we know that, the property losses we are talking about. Yeah. So now it says that, if there is an earthquake of the intensity, say. Okay, so if there is any earthquakes of intensity some 5, so some base of the property loss basically. So this is the mean value of property losses in a given city. Okay, some 2.5 million, some dollars. And then we know it's a standard deviation also. So this is the 1.5, the million, you see, the dollars. So these are the property losses. Then we have business loss also. Okay, so the business loss also, these are all random variables. So the mean value is, some $60 million. Okay, then the standard deviation. So the business loss is, some 2.5 million, say. Okay, now similarly you have injuries also, that is some health issues are there, so the losses due to injuries actually. Okay, so that is, let us say its mean value is some 2 million. Okay, so these are just some numbers, and then standard deviation, so this is the mean value, the standard deviation, say. So this injuries is, some $4 million. Okay, so these are individual things. So whenever there is an earthquake, say, so somebody says you can have a property loss, you can have business loss, or you can have injury loss, and there are, their individual mean values. Okay, now if you want to ask the question, so what will be the total loss? And let us say here, somebody says that the correlations also, the cross correlation also. So this business and the property, so they are correlated with some 0.7, and the property loss, injury loss, say, the correlation between our the between business, this is 0 actually. Okay, so what they say is, so this and this are correlated, but this thing is not correlated with property or neither business loss. Okay, so these details have been given to you. Now if somebody asks you to find out, you see, the total loss during an earthquake. Okay, and now what will be the total losses during an earthquake? So now in earthquake we are having three type of losses. So the total loss will be, now what will be the total loss now? See, when an earthquake occurs, you can have a property loss, you can have a business loss, you can have injury loss actually. Okay, so three type of losses are there, and these three are random variables. Some normal random variable, you know their mean value, standard deviation, other things also. Now we have to find out the total loss. So what will be the total loss? Yeah, total loss, how do you calculate? Yeah. So what will be the total loss? You know, three type of losses are there. So the total loss will be
summation of all the losses, sir.
sum of all the losses. So the property loss plus business plus the injuries actual. Okay, and now these three are random variables basically. So now these three are random variables. Say so this also will be random variable. So obviously it also will have a mean value. So mu of t. So this will be simply the individual the means itself, the mu b plus mu injuries actual. Okay, so you add all those numbers 2.5 plus 6 plus 4 or whatever, so this turns out to be 12.4. Now it also will have a variance you have to find out. So now for finding the variance, say, so last class we have already seen. So if we are having n random variables, say, and if y is a new random variable which is the sum of all these individuals, so this is the mean value and this is your variance value. Okay, but only thing here is you will have a covariance term will be there. But now we are assuming that in this problem, property and business are correlated. Other things are not at all correlated itself. Okay. So this turns out to be 1.5 square plus you see 2.5 square plus 2 square plus 0.7 is the correlation. So multiplied by 1.5 into 2.5. So finally it turns out to be some 17.75 million. So this total loss, say, so this will be, you can find out by this square root of this quantity itself. Okay. So these how the total losses, you can find out, so this type of problems basically. Okay. Now let us have some more, the problems we can do to have more, the better understanding. Yeah. Say like for example, say this is a very, the interesting structural engineering thing. So generally in our structural engineering, say, okay, so if R is the load carrying capacity, okay, so R is the load carrying capacity. So the load carrying capacity, let us say we denote by R, okay, and then Q, say, is the demand or the load effect basically, or the demand. So this we also call this as resistance. So we have a load and we have this resistance here. So now generally you see we define the performance function. Okay, so what do you mean by performance function? In our structural engineering we have load and we have the resistance. Say how do we calculate the performance? So if I denote by this y, okay, so now how do you find out safety and other things? When your structure is safe, you have the load and you have the resistance actual. So what is your criteria? Now the criteria will be, now what will be the performance function?
Greater than load.
Now that should be obvious, it should be greater than this one. Or if you write say R minus Q, okay, so when you can say that the surface, when the structure is safe, so R is resistance and Q is the load. So we say that our safety is governed by
Should be greater
R
than.
greater than
no,
R
why
by
should be no, why should be greater than 0? Then only we can say that our things are fine. Now here also so like for example if R and Q say they are all random variables. Okay, they are all random variables are there say. So now what happens, our performance, this y also will be a random variable. So it also will have, suppose if I know mu r, then sigma r, say, then mu q, then sigma q. If I know their individual mean values and then their standard deviations, so I can also find out mu y is equal to, so mu r minus mu q. So you can easily find out from this expression. And then the variance, say, that is my sigma y square. Okay, so this will be that expression already 1 to, you see, if there are n random variables say, okay, so you can write this as j is equal to 1 to n, so ai into aj. Okay, so covariance of xi, you see, xj. Okay, so there are n random variables. Like you see, if I write y as the previous expression only. Okay, so this expression only we are writing here. So this expression you can combine this with this also. You have to include I is equal to 1 to the, or you can write it separately saying that this is valid only when I is not equal to j. So using this expression, say we can easily find out so this becomes sigma r square plus sigma q square. Now because of this negative thing is there's a minus 2 times the covariance function of r and q. So this is how we get our expression r. We can also write this as sigma r square plus sigma q square, say minus 2 rho rq. Okay, there's a correlation coefficient between both of them, sigma r multiplied by sigma q. So this is our covariance basically. Okay, now in generally what happens, what type of correlation will be r and q generally in our practice? Resistance and loads, so what will be the correlation between them, whether there will be any correlation or what will happen? So the
Negative.
capacity, they will be highly correlated with each other, or they will be uncorrelated. What is that one?
So they will be negatively correlated.
So in reality, what happens? Negatively correlated load is increasing this one. See the load which is acting on your structure, it is governed by the resistance. So generally, in most of the problems, what is that we try to assume? What will be the correlation between load and resistance? See, in most of the cases, what happens? Load, whatever load is coming on your structures and your resistance, both of them will be basically. The resistance of a structure depends on this one. Some arbitrary random load is coming. Say, what happens? So,
So they,
hmm.
so
So
resistance
generally.
depend on load.
No, that is fine. But generally, what do we do actually? Okay, whatever the load comes, your resistance, if the load is small, that doesn't mean that your resistance will increase, right? Or you will decrease your resistance or whatever. So generally, in our structural engineering, so if you see many of the problems, this is generally, we assume it to be, zero correlated or uncorrelated kind of thing. Okay. So if there is uncorrelated, say, so then this becomes simply a sigma r square plus sigma q square. So this is how we calculate our this one. Now here one more important thing also we can calculate, that is a coefficient of variation. Okay, so this also is a very important thing. So this coefficient of variations, it is basically a non-dimensional quantity. Okay, it is a non-dimensional quantity. It is just defined as the ratio. Okay, the coefficient of variation CV also sometimes we call, or V of y. So it is something like the ratio of standard deviation to mean value. So this is how we define this coefficient of variation. So the units will be there are no units basically, because mean also will have the same units, standard deviation also will have the same units. So now in this problem set, so your numerator basically, okay. So this is sigma r square plus sigma q square minus 2 times say covariance of this r and q. This will be, you see, mu r minus mu q. Okay, so this is our coefficient of variation also. Now sometimes of course we will introduce after some point of a time the reliability index. Okay, so reliability index we say, which is denoted by this beta. So this is generally defined as a reciprocal of this coefficient of variation. Okay, so V of y, so this will be mu y by sigma of y actual. Okay, we will define after some point of a time. You will understand what is the physical meaning of this reliability index and other things also. Okay, so these is how we can calculate in our for general problems. So now let us take one simple supported beam, say. So I have a simply supported beam, which is subjected to UDL. Okay, so this UDL is W, and then you also have a concentrated load also, some P. So let us say the length of this span is some 20 feet, say, of this beam. This load is acting exactly at the center, this concentrated load. Okay. So these are my simply supported beam like this. So now we say that the load and the resistance, both of them are random variables. So they are all the random variables, and let us say we assume that they are all normal random variables. The advantage of normal random variable is only mean and standard deviation are sufficient, okay, to know the entire thing about the thing itself. Now we define so the details have been given. So W, so there are two type of loads are there. One is UDL, other one is this concentrated load. Both of them are random variables, and even the beam's resistance set, this is also a random variable, okay, and their mean values are like this. So W, so that is a mean value of the UDL set. So this is one, some units are there here. Then it's a coefficient of variation, or this standard deviation say is zero point 0.1 times k by 4 times, okay. Or sometimes in some textbooks they also write this coefficient of variation. So coefficient of variation is generally just sigma by mu, okay, just that is also sometimes widely used actually, okay. So the coefficient of variation, say let us say it is 10%, that is 0.1, okay. You can find out the ratio between these two also. Then for the concentrated load, say, so the mean value is 12 times this one, and its standard deviation, say, is 1.8 times okay, and then its coefficient of variation, okay, is some 15%. You can find out the ratio itself will tell you. Now the resistance is say the bending resistance of the beam is so this is also random variable. We say 200 this one, and then it's a standard deviation, say, okay. For the resistance is 24 times some k foot or whatever, and then its coefficient of variation, okay, is some 12%. So anyway, this is not required. Sometimes both of the all of the interlinked with each other only. So sometimes in textbooks they will give you coefficient of variation, which is nothing but the ratio, okay, which is a non-dimensional kind of a quantity. And now we have to find out the probabilities in this problem. So the probability that the beam will fail. Yeah, the probability that you see the beam will fail. Yeah, so this is what we have to calculate. Okay, so now so as already we said, so you are having a simply supported beam subjected to a concentrated load, and then subjected to a UDL, and then the span and other details have been given, and the problem is load, resistance are all random variables, okay, even the the resistance also, and all of them are normal random variables. So this has been given to you, provided, and the bending, these are the statistics has been provided to you. Now you have to find out what is the probability that this beam will fail itself, okay. So now how do you calculate this one? So what is that you have to do in this problem? So what do you mean by failure here? And there is only, we are talking about the bending resistance only. No, you forget about shear and other things, okay. They're just the moment resistance only. Now, so what do you mean by failure here? Now, so what is meant by failure? Like in the previous problem we have seen, right? What do you mean by failure here? Yeah, so this is a simple bending resistance is there, load also So what do you mean by failure? Now what do you mean by failure here?
The mean of bending moment of beam greater
Bending
than
moment? Yeah. So the bending moment coming from the loads, say, if it is more than the bending resistance of the beam, then what happens? See the bending moment which is coming from the loads, okay. So if this is more than the bending moment which comes from the resistance, what happens?
because beam will
Automatically this will reduce. This is failure, okay. So this is how you have to calculate. So now you have to find out the bending moment. So now here you are having two loads are there. One is a concentrated load, other one is the UDL itself. So now the bending moment, say, due to the UDL is anyway WL square by 8 itself, okay. So now WL square by 8. So now span L that is 20 feet. So 20 into 2400 divided by 8. So this will be 50 times the W. So this is a bending moment due to the distributed load actually, okay. Now if you try to find out, say, the bending moment due to the other load, Okay, that is a concentrated load. So you know all these things from your analysis. So PL by 4. So this also turns out to be, 5 times P. So this is a bending moment due to UDL and the bending moment due to the concentrated load. Okay, now we define our performance function. Now what will be the performance function? MR is my, the moment due to the resistance actual. Okay, and now what will be the performance function now? Y will be now what will be Y? So I know MD, I know ML, that is from the concentrated load, and I know MR, that is from the resistance. So now what will be the performance function? Y will
So
be
MR minus MD minus ML.
MR minus MD minus ML. So it's just straightforward. So you substitute all those variables, say, okay. So MR will be there. So MD is 50 times W, and ML is 5 times P. So this is my Y. Okay. Now here we are saying that now what type of random variables are this? All of them. We have said that these are all normal random variables. Okay. So load is normal random variable. P is also normal random variable. Moment of resistance is also normal random variable. Now what type? Now W is normal random variable. P is not normal random variable. So what type of random variable will be MD and ML? What type of random variables are there?
So normal random.
Why they will be normal? What type of transformation is this? How MD depends on W, or how a bending moment depends on the load? So what is the dependency? Why they will be normal? See, what type of random variable is MD and ML? They are normal only, but how? See, why they will be normal? So how they are related to each other? Like you see how MD and W are related.
So there is linear transformation.
So it is a linear transformation. So now normal distribution already we have said actual. Okay. So the normal distributions are closed under linear operations. We have already said this long back. So because of linear transformation, say, so automatically, MD and ML, all of them also will be normal random variables itself. So now it will be very easy to calculate the details actually. Okay. So this is my performance. So Y is, so this whatever expression we have written here, MR minus 50 times W minus 5 times P. Okay, so this is our expression. So now we have to find out the probability of failure. So for that we have to find out mean value of Y. So this will be mean value of MR minus 50 times the mean value of W minus 5 times is the mean value of P. So substitute all these numbers, say 200 minus 50 into 1, okay, minus 5 into, you see, 12. So all these numbers have been provided here. One, all the numbers are there available here. So substitute here. So this turns out to be 90. So this is the the mean value of Y. Now we also have to find out the standard deviation also, sigma Y square. So this will be given as because there is no correlation, say. So right now in this problem is they are all uncorrelated actually. Okay, because no, they have not specified this correlations. So they are all uncorrelated with each other, because a concentrated load, how much concentrated load it comes, how much will be the UDL, and how much will be the resistance, say. Generally they all will be highly uncorrelated. So use this expression. Okay, so with this expression you can use, and then you can find out the variance of Y itself. Okay, so now if I substitute all those numbers here, so this turns out to be so AI square sigma mi square. So substitute all those things. So 1 square sigma square mr, and of course minus 1 is there here. Okay, so sigma square m of d plus minus 1 whole square, so sigma square m of l. So substitute all those things. So 24 square plus 50 times sigma w square plus 5 times sigma p whole square. Okay, so dump all those numbers say. Okay, so 24 square plus 5 square plus 9 square. Okay, so this turns out to be some 682, k times this kft whole square. So now it's standard deviation. Say you take the square root of this expression. So this turns out to be 226.1 k feet. Okay, so this is our standard deviation. Now you can find out the coefficient of variation, which is nothing but the ratio sigma y by mu of y. No units for this expression. So this turns out to be 26.1 by 90. So this is 29 percentage basically. And then the reliability index is saying, which is reciprocal of v of y. Okay, so this is 1 by 0.29. So this turns out to be, you say, 3.45. So these are all the statistics actually. Now you know the mean value of y, you know the sigma of y itself also. Now you have to find out the probability that beam will fail. Now how do you calculate this probability? When the beam will fail. Now you know the performance function also. What is that you have to calculate? Now what do we mean by failure here? How do we calculate this expression? Now, how to write that probability? Probability of now, what should be inside? Yeah, what is the probability you have to evaluate? Now, what is that you have to calculate? So, probability means now. So, when beam will fail?
Y less than 0.
Y less than 0. So this is what you have to calculate. And y is a random variable, and and it's a normal random variable because all are linear transformations only, and its mean value and its standard deviation. Okay, so probability of failure is essentially so we are calculating probability of y less than 0. Okay, so probability of y less than 0 means you have to use that standard normal table. So this is x minus mu by sigma. Okay, so y by sigma of y. So you know all the details. So now you can see the mean value, the number is 0, x minus mu by, we write like this, right? X minus mu by sigma, and because where x is 0, so we are interested in this one. So this turns out to be mu by sigma. What is the ratio of mean to sigma? See this expression. Ratio of sigma to mean is what we are calling. We are calling this as coefficient of variation. Reciprocal of coefficient of variation is the reliability index we are calling. Reciprocal of coefficient of variation will be simply mu by sigma actually. Okay, so now this mu by sigma is essentially your reliability index basically. Okay, so this so this turns out to be phi of minus 3.45. So this you can see from the standard normal table. You have to find out from that area. So this turns out to be 0.28 into 10 to the power of minus 3, or this number will be 0.000280. So this is the probability, okay, of the failure itself. Or if you want, you can even write this expression. If you can draw also. So what we are doing is it is basically a normal distribution. So this is my py of y. Okay, so this is my 0. So I'm finding the area under this small curve actually. Okay, so this is my probability y less than 0. So this area is 0.000280. Okay, so this is how we calculate the probability of failure of our beam itself. Now, what is your comment? This probability is high or low, or what is your comment about the beam? Whether it will fail or whether it will be there? Now, what is this probability is high or low?
Probability
Now, probabilities
It's very good.
it is very low. You followed, right? So the chances of the beam to fail is very small. That is how you can you can, this is how you can interpret. You followed. Suppose if this probability is 0.5 or 0.6 say, then definitely you see the beam will collapse actually. Okay, so this is the mean value. So if you want to draw in a pictorial this one, so this is a 90. So this is how the probability density, and we have found out this area actually. Okay, now here some more things will be there. Like suppose sometimes we will be having this log normal random variable say. This also is straightforward. Okay, log normal random variables are there. Let us say we have some function y, which is we write as k x1 x3 by x2. So all are log normal basically. Okay. So x1 x3 x2, they are all log normal random variables. So these are all log normal random variables, and of course k is some constant. Okay, so this type of problems also will be there. Now here the advantage of log normal random variables here. So if you look at this expression carefully, okay, y is equal to k x1 x3 by x2. If you take logarithm on both the sides, so if I take logarithm, you see on the both the sides, say, okay, so we can write this expression as log y is equal to log of k plus log x1 plus log x3 minus log x2. So this will be like this actually. Now what type of random variable will be log x1, log x3, and log x2? If x1 is log normal, say what will happen to log x? See, x is a log normal random variable. Okay. What will be log x? Yeah, what type of random variable will be log x? Now what type of random variable? Previously we have discussed, right? See, if x is log normal, so what will be log x? See, previously we have seen, right? If x is normal, say e to the power of x was no. See, if x is normal, what will be e to the power of x? What type of random variable it will be? Now, what type of random variable is e to the power of x? We have done, right?
So log normal.
A log normal. Now you tell me, if x is log normal, so what will be log x?
So normal.
You just use the same expression. You followed, right? If x is normal, e to the power of x, this one, so automatically this gets cancelled actually. Okay, so this turns out to be normal random variable basically. Okay, so generally when you are having these type of transformations, say y is equal to k x1 x3 by x2, and these are all log normals, say. So then you can transform and then use the same, the normal distribution itself. You followed. Now let us see one example, which is of course more or less related to the previous one only. So if let us say we are having a same beam, okay. Let us say it is a some steel beam is there, okay, and let us say it is a compact section. I hope all of you know, right? What do you mean by compact section? Semi-compact, slender. You would have done in your steel design. So which will reach, that the plastic movement and other things. Plastic hinge forms and it can take all those things. So its movement capacity. So the plastic movement capacity is given by Fy into Z, where Z is a plastic section modulus. Okay. So this is for a compact section. Okay. And now Fy is the yield stress. Yeah. And let us say the load basically. The load is some total is a Q, and this is also a random variable, the maximum movement demand or whatever say. Yeah. So let us say Q indicates some movement demand. Okay. So on the steel beam. Okay. Now we assume that generally, as already I told you, in most of our engineering say, all our variables, whatever you deal when you in design, they are all positive quantities only. Like yield stresses, say they cannot be negative or anything like that. Or the loads, all of them will be positive only. So there is no negative kind of a thing. So generally, all positive quantities, say we model them as the log normal random variable. So this also we use generally. Okay. So now so we want to calculate these are the numbers, and let us say we have the numbers also. So for Fy, So the mean value is 40 times some KSI, and its a coefficient of variation say is a 10% actually. Okay, and then for the load, the section modulus. So the section modulus is also random variable, and its mean value is some 54 inch cube or whatever, and its coefficient of variation is 5% actually. Okay, and then the load basically. So this is also a random variable, and it has a mean value is 120 k times ft, and its coefficient of variation say is 12% actually. So these are the details. Okay, the mean and standard deviation of all these random variables, and all of them are log normal random variables basically. Okay, now we want to find out the performance function, or the probability of failure and other things say. So like this, I want to find out the probability of failure of my beam. Yeah, failure of this steel beam. Yeah. Now what will be the performance function here? So now I have my compact section. I know its resistance, and I know the random variables, and I know the load also, which is coming through this Q. That is a moment, demand, or whatever. And these are the given. Now and we want to find out probability of failure of the beam itself. Only the difference between this problem and the previous problem is this problem has all of them. We are assuming them to be log normal random variables. And now what will be the performance function here? See, how do you write the performance function? Y? Now, what will be the performance function here? Y?
P minus
Now, y will be?
MP minus Q. MP minus Q.
MP minus Q. You can also write like this. But the problem what you have here is, what type of things are there? What type of random variables are these?
Log normal.
Log normal. So you can write MP minus, that Q or whatever. This also you can write. See, the intelligent way, this also is fine. And then you can say failure means y less than 0. Other way of doing things here is, you can also write this as y is equal to, your MP by Q also. Now what will be the failure? So I can write like this also. And failure means y less than 0. I can also write like this also. What do you mean by failure here? If I write as a ratio, say, what do you mean by failure? Both of them are same only. No.
Should be greater than 1.
So it should be less than 1. You follow. So MP should be less than Q. You follow. That is, the plastic capacity, if it is less than the load, say, then automatically, the failure basically. So you can write like this also. You can write like this also. So some type of problems say that may be beneficial. Sometimes this also may be fine, but both of them will be same. So y is equal to MP means fy times z itself. Okay, so we write this fy times z by q. So this is my y. Okay, so probability of failure say. So this is nothing but probability of your y less than or equal to 1. So this is how we write this one. Okay. And now we have said that all of them are log normal random variables. So this also is log normal. This also is log normal. All of them are log normal. Okay. And now what happens is, so now we have to find out y itself. So now the intelligent way of doing things, as already I told you, if you take logarithms on both the sides, okay, so they automatically, so this turns out to be, log y. So log of f of y plus log of z minus log of q. Now what type of random variable will be log of y, fy, log of z, log of q? Basically, they are log normal. So if you take logarithms, say what type of random variable that will be?
Normal.
Normal random.
So they are all normal random variables. So now what will be what type of random variable will be log y? So these are all normal random variables when you take logarithm. So what type of random variable will be log y?
So normal
So what type of random? This also will be
normal random variable.
because of why it is normal. See why it will be normal log y. What type of transformation is this? See, what type of transformation is this? This is one random variable, this is another random variable, this is another random variable. How log y is linked to x1, x2, x3?
It's addition.
So what is that type of transformation is this? Addition is nothing but?
It's a linear.
It is a linear transformation. So when you are adding something linear, say automatical output also will be normal random variable only. So this is my log y. Okay. And now I will find out, you see, mu of log y. Okay. The mean value say. So this will be simply mu of log of f of y plus mean value of log of z minus, you see, the mean value of, you see, log of q itself. So this is my mean value, and I can also find out its standard deviation only. So instead of working on y, we are all working on log of y itself. So this also will be sigma square log fy plus sigma square log this z minus sigma plus sigma square say log of the q. So this is my standard deviation. So now only problem what we have is we have to find out. See the input data with the data has been given. So this is the mean value of fy, coefficient of variation. Anyway, if you can find out the standard deviation. So all the mean values is say. So they have been given for fy, z, and then q actual. But now in our calculations, we require mean of log of this quantity, mean of log of this quantity, mean of log of this quantity. So this has to be calculated. So last time you followed it, we have this when we discussed about log normals. I have given, I think, those equations are there, how to compute. You remember those equations? See, when we discussed about log normal, how to write, say. See, we have already, when we discussed about log normal, okay, so we have given that one. Where was that? See, normal was there, then log normal was there, yes. Okay, so now you can see these expressions. Now, so you can see here. So now if I have, the mean value say, so long back, we have written this one. So sigma square log y will be, log of vy square plus y. Then mean value say is given by, you see, mu of y. So we have written all those expressions previously. So you have, by knowing the mean value of y, then the standard deviation say. So the if I know the coefficient of variation, that is vy whole square. So automatically, I can find out sigma square log y. Substituting here, so I can find out the mean value. So now you have to use this expressions, okay, to calculate our numbers. So previously also we have done this type of thing. So you can see previously also when we did the problems, we know the individual mean values. Now in log normals, we found out sigma square log y, then mean value of y through these expressions, okay. So these expressions have to be used here also. So this is the only, the change here. Okay, other things are all same. Now let us go back to our problem. Now, so this you have to find out actual. Okay, so the sigma square, the log of y. So I will write one. Other things you can easily find out. So log of 1 plus v fy square. That is nothing but the ratio. So log of say 1 plus the 0.1 whole square. So this turns out to be 9.95 into 10 to the power of minus 3. And then the mean value, say mean of log of f of y. Okay, so that is at m hat or whatever I have written there. So log of mu of f of y minus 1 by 2 sigma square. Sorry. Now the same expression only, sigma square log f of y. Okay, so this turns out to be 3.68. Now similarly, say, so you find out all other quantities. So log z, so this turns out 2.5 into 10 to the power of minus 3, and the mean value of log of z. So this turns out to be 3.99. Then sigma square say, okay, log of q. So this is 1.43 into 10 to the power of minus 2, and then mean value of log of q. So this turns out to be 7.27. So these are our numbers actually. So this is the extra thing which you have to do. So generally in the data, they will give you the mean value of f, y, z, and q. But then when you are doing the transformation, say, so you have to find out these numbers actual. Okay, so you calculate all those things. So now the mean value. Okay, so mean of log y. So this turns out to be 3.68 plus 3.99 minus 7.27. So this turns out to be 0.4. Okay, and sigma squares of log of y. So this also we can calculate. So you sum up all those individual variances, say. Okay, so this turns out to be 0.0268. So this is a standard deviation. So the variance actually. So log y will be, you take a square root of this expression. So this turns out to be 0.164. Okay, so this is what we have to calculate. So now the probability of failure. Okay, so this is a probability of y less than 1. Okay, so y less than 1 say is same as no. So now y less than 1 is equal to what? So now what type of random variable is y? Y is basically a log normal random variable. Okay, but our when you take the transformations, a logarithm or whatever, so it turns out to be a normal random variable. So now how do you calculate this probability? Now probability of y less than this has to be calculated, and now this you can do it in terms of see y less than 1 is equal to what? See probability of y less than 1 I can write in terms of log y. Say what is that equivalent to? Y less than 1 is equal to log y. What do you mean by failure when you write in terms of log of y? See this expression. See y less than 1 is with respect to this one, that is meant by failure. Now we have done a transformation. So now you have converted all of them into normal random variables by taking a logarithm. And now what do you mean by failure when if you look at this expression? Now see what do you mean by failure when you write in terms of log of y? So what is meant by failure here? So this is my resistance, this is my demand, that is the load which is coming here. So now what do you mean by failure here when you write the expression like this? Now what is failure here?
So less than 0 is failure.
Less than 0 only, that's all only. Okay, so this is, so y less than 1 is same as saying log y less than the 0 kind of thing. So what type of random variable is log y? Already we have said log y is a normal distribution. So this turns out to be same the standard normal distribution. You go log y anyway, it is 0 minus mean value of log of y, okay, by standard deviation of log of y. You followed. So this turns out to be 5. Yeah. So it's straightforward. So 0 minus 0.4 by 164 comes here, and then you dump all those numbers. So the reliability index is minus 2.4. So this turns out to be 0.82 into 10 to the power of minus 2. So 0.0082. So this is the number. Or if you want to type it in a pictorial kind of format, say. So this is as good as saying this is y. So we are saying y is a log normal random variable. So this is something like this. Okay, so this is my y. Now what we are doing is my failure is this one. So this is the area. So the area under this curve is 0.0082. So this is my failure of my steel beam actually. And now what is your comment? Whether this beam will fail or it will not fail.
So here also failure chances is very low.
Very low. So 0.0082 means it's almost the beam is perfectly safe actually. Okay, so the same problem set. So now the failure means so when you are looking at the problem, so you have to decide. Okay, so you can write in terms of like a demand minus this one, or you can also write like a ratio If you write like a ratio set, so then failure will be y less than 1. If you write in terms of the subtraction addition kind of a thing, then it becomes y less than 0. So it depends. So in some problems this may be convenient, some problem it may be convenient, but finally the end is you have to convert everything into a normal thing, say, then things will much more easy to calculate. Okay, so this is how you can find out. Okay, so there are so many problems you can solve. Now let us see the extension only, the nonlinear transformations. Okay, so when there are nonlinear transformations of random variables, now what will happen to the moments? Densities already we have seen, but the moments. Okay, so like for example, you see I have a function y say, so this is I have an initial random variables x1 x2 up to xn, so these are all random variables. Now I have a function y which is a function of all these random variables, and we are saying that this is a nonlinear function. So this is a nonlinear function. So now what will be the mean value of y, the standard deviation of y, I have to find out from this nonlinear transformation. So now how do you calculate when you are having a nonlinear functions? Now, and you know their individual means. Okay, so mean values, mean of x1, mean of x2, and their standard deviations also Now we have to calculate only what will be the mean value of y, the standard deviation of y. In all the previous problems, say it was all linear transformation, so it was all straightforward actually. But now we are having a nonlinear function, like you see x square or x cube or square root, and so many things are there. So now how do we do this? How to calculate the moments of a random variable when the transformations are linear itself? So how do we handle this problem? So this is a very important, the transformations actually. Okay. Now what do we do in mathematics? So whenever you see any nonlinear functions. In mathematics, how do you solve when you see any nonlinear quantity? We use some kind of expansions. Okay. So what type of expansions we use? See, whenever you see a nonlinear function, so what do you do in an ordinary mathematics? So what type of expansion we use? Now, what do we do? What is this expansion? Now, what is this expansion? What do we do? Now, what is this expansion known as? See, any nonlinear function you can expand in terms of no. See, what is this expansion known as? I have written the expansion also. So what do we do?
E raised to x expansion.
So e raised to the x expansion. Where is e to the power of x here? There is no e to the power of x, right? What do this transfer? This expansion known as? See, whenever you see a nonlinear function, so how do you solve in mathematics? When you have a nonlinear function, what do? You linearize basically. So now to do that one, what is that expansion we use? This expansion is, see, what is expansion for f of x plus h? See, if I know f of x, say, okay, and now if I want to calculate f of x plus h, how do I calculate? And if it is a nonlinear, so how do you calculate this x plus h? So you have done mathematics, right? If you know f of x, how do you calculate f of x plus h at some slight perturbations? How do you calculate? What type of expansion you use? See, have you heard this Taylor series expansion?
Yes, sir.
Now, what is this? See, whatever I have written above, what is that it is? So what is f of x plus h? You know, right? F of x, you remember h f dash x by, this one plus h square by 2 factorial f double dash of x. What is this Taylor series expansion? What is that you try to do? So whenever you are having a nonlinear function, if you want to calculate, say you expand in terms of Taylor series only. You followed. So now here, whenever you are having any nonlinear transformation or nonlinear function of this type of thing, say, what to do is you can write in terms of a Taylor series expansion. So now this step, so now you have, when you do Taylor series expansion, you have to do around some value, that is x or whatever. So here what you are doing is you are doing a Taylor series expansion at its mean values, because the mean values are already known. Okay, so you do the Taylor series expansion around the mean value, say. So you do expansion, you write the Taylor series expansion, and then you can calculate the mean value, standard deviation, other things from this expansion things only. So like for example, say we will just see this one. So like same beam problem we will see. So now as already we said, right, the performance function or whatever, so for rectangular beam, say. So we are having a beam which is a rectangular cross section. Okay. So now the same thing. So y is fb, that is some whatever this one, minus m by s, the section modulus or whatever we are having. So now the section modulus. What is the section modulus for rectangular cross sections? Right? So suppose if b is the width of the beam and d is the depth of the beam, say. So its section modulus will be right, bd square by 6 actual. Okay, so this performance function I can write this as f would be minus some 6m by bd square. Okay, and fb is allowable bending stress. Same problem only, whatever we wrote previously. So if fb is allowable bending stress, say. Okay, so minus m by s. So a bending moment m is there, and then bd square is there. So now so this is my performance function. So now if all of them are random variables, say. So now if fb, then m, then b, then d, all are random variables. And let us say their mean values I know. So mean value of m is some 10,000. Okay, so 1 lakh actually, almost it is. Okay, some lb inch, whatever this one, and it's a standard deviation or coefficient of variation. So this is a 12,000. And then the mean value, say, of my allowable bending stress. So this is a 1600, say, some psi, and then its standard deviation. Okay, is a 512 some units. Then we have the breadth of the beam. So this is a 5.6 inches, and it's a standard deviation, say. So this is a 0.224 inches are there. And then you also have the depth of the beam. So this also is random variable, and its mean value is 11.4 inches. And its standard deviation, say, is very small, so 0.342 inches. So these are the random variables. So now we have to find out, the probability of failure or whatever quantity we have. So now what type of function this is? Now how this y is depending on the random variables? So what type of function it is? So y is a function of fb, then we have m, and then we have b, then we have d. What type of transformation is it? Is a linear transformation or it is a non-linear transformation? So what type of transformation is this? Now what type of transformation is this one? Is it a linear or non-linear transformation? It is
Non-linear.
So now when you are having a non-linear transformation, so what is that we have to do?
We need to use Taylor series.
So now you have to expand Taylor series, but when you expand the Taylor series, say, you have to expand around
Around mean, sir.
around the mean value. So this is the first step you have to do. Okay, So now use the Taylor series expansion here. So now you should know how to write the Taylor series. Okay, so you write, of course, we neglect the higher order terms. So here also, if I include only the first order terms, first order reliability, second order reliability, other things are there. Right now we will we include only up to first order terms. Okay, so now let us write the Taylor series. So you know how to calculate the Taylor series. So this turns out to be the mean values of FB minus 6 mu of M by mu B into mu D square. So dou F by dou F of B. Okay, so evaluated at the mean value plus, so M minus mu M dou F by dou M evaluated at the mean value, so plus B minus mu of B dou F by dou B, okay, at the mean value plus D minus mu D dou F by dou D, okay, and which has to be evaluated at the mean values. So this is nothing but that you have to find out the derivative, and then you have substitute the mean value. The substitute the mean value. So this is what you followed, right? You have to do. So now you calculate all those derivatives. So dou F by dou B, this is 1, and then so, and you have to evaluate, this is also 1. So dou F by dou M, so this is minus 6 by BD square, and then you have to evaluate this at the mean value. So dou F by dou M, and if you evaluate at the mean value, say minus 6 by, what is the mean value? So mu B mu D square. Okay, now similarly say, so dou F by dou B, so this turns out to be 6M by B square D square. So you have to evaluate at the mean value. So dou B, you have to evaluate at the mean value. So this will be replaced by 6 times mu of M by mu of B whole square, and then mu of D whole square. So like that, you calculate all those numbers itself, say in this expression. So dou F by dou B, then dou F by dou D also you can write, and you have to evaluate at the mean value. So this turns out with 12 times mu of M by mu B mu D Q. Okay, so now if you substitute all those mean values, everything and then substitute in this basic expression. Okay, so finally I will get my Y as FB minus 0.00824 times M plus 147.2 times B plus 144.6 times D minus 2473. So this is the final expression actually. Okay, and now you tell me, now after this, but we have included only of the terms up to first order. Yeah. Now you tell me, suppose M, F, B, all of them are normal random variables. Say what type of normal random, what type of random variable will be Y now? See, originally the transformation was nonlinear. What was Y? Y was FB minus 6M times BD square. Now, after expanding in terms of Taylor series, so this expression has been converted to this type of format actually. Now, tell me what type of random variable is Y?
So Y is normal random variable.
Why it is normal random variable? Because now your nonlinear transformation has become
Linear transformation.
But here you have to keep it in mind. How did we made it linear? We have expanded in terms of Taylor series. But in Taylor series expansion, you will be having all terms up to higher order terms, second, third, all up to infinity it will be there. But how did we do this linear? The linear assumption, what is that we have ignored here in the Taylor series expansion?
Higher order terms.
So if you ignore the second order, if you suppose if you include second order, then you may have some non-linearity also. Okay, so if you include only after terms of first order, say, so you have converted your non-linear transformation into a ordinary, the linear transformation. So now you can say Y is also normal only. Okay, and you can use the same procedure. So mu of Y means you dump all those the mean value of FB 0.00824 mean value of M plus 147.2 times mean value of B 144.6, a mean value of D minus 2473. So substitute everything. So we will get a 775.4, and then the standard deviation also. So it is straightforward. So you can substitute all those numbers. So you will get this as a 275.465, psi, and then sigma of y side. So that will become a square root 524.8, not point, I think is the comma. Okay, so you substitute all those things, so you will get this. And the reliability index, which is mu by sigma. So this turns out to be 1.48 actually. Okay, and the probability of failure will be no. So if you want to calculate probability of failure, say now what is the definition here? So when you say it is a fail,
Y less than 0.
0, because it is all summations and other things. Okay, this entire thing, if it is this one, so you can easily find out actually. Okay, so you can solve like this also. So whenever there is a nonlinear transformation, say, so what we try to do is whenever there is a nonlinear transformation, so now you convert into a linear transformation. So the technique, that the trick what we are going to use is you followed, right? You do a Taylor series expansion, you include terms only up to first order, you will get this one. But you can ask now, you see, suppose you have made a mistake here, you followed. So whether you will be accurate enough, or if you include the higher order terms, what happens, so that we can, we will check it later also, okay, the accuracy of this procedure. But this is a general procedure we use whenever you see a nonlinear, the transformations, okay. So this is how we handle these things in practice. Suppose, there may be some cases where, after doing a Taylor series expansion also, still things will be more nonlinear, or your Taylor series may not be accurate also. Then how do we handle is a big issue. So one simple thing what we do is, this Monte Carlo simulation. This is the most, I should say, the simplest kind of thing. The Monte Carlo simulations also we use. The advantage is, whether it is a linear or a non-linear, it is all straightforward actually. So the concept is, you break it into several, you solve several deterministic problems. This is a straightforward, the Monte Carlo simulations we use. Okay, so whenever you see any random things, say, so now instead of doing one simulation you followed, you solve, you generate random numbers on computer. This is the most popular thing. So you generate random numbers on computer, and then you see. Okay, so then you solve several deterministic problems, and then you will get the solution actually from the numbers. That is numerically you obtain the probabilities. Probability and whatever you want, say, you obtain numerically itself. Okay, so anyway, so I will stop here. We will continue our next class through this this Monte Carlo simulation. Okay, so if you have any questions, you can ask me.